Uh, so today, okay, sorry. All right. I will try to keep my research focus on this topic of single nanowire electrochemical measurements during lithiation for nanoelectrode materials. I know the workshop main topic is on characterization. So this is something that I have performed during my PhD, where I was focusing on nanoelectrode materials and then further trying to analyze some characterization techniques to the betterment of the research community. Feel free to stop me anytime you have questions, or we can have a question session anyway at the end of the session. All right, so here is a brief outline of my research. So I figured out that it would be better to give a small background on batteries, understand what goes on in a battery, how it works, and the mechanism involved in it, and further drag on to bring my technique that involves understanding how a single nanomaterial performs in these batteries, and then characterize several techniques to measure the electrochemical, electrical, mechanical material properties for the nanowires involved in batteries, and further conclude with a degradation study that was done for the very first time on a single nanomaterial. So to begin with, as everyone use their laptops, cell phones, lithium-ion batteries everywhere, it's readily available, it's currently cheaper. The main advantages, speaking in terms of its technical challenges, is it is lightly electropositive, and it is lightweight in nature. That's why your phones, the batteries in your cell phones are really lightweight in nature. Along with that, they have high energy density, and on top of that, they can be manufactured into different shapes and sizes as you want. Now, further, if you think about in a battery, we have different pieces in a battery. You have electrodes, you have cathode, anode, then you have your electrolyte, and you have binders. Then there are several other fillers that you want to add in for safety and quality of your battery. Now, the way the battery works, we call it as a rocking chair mechanism. During charging of a battery, you have these lithium ions that move from cathode to anode, whereas during a discharge of a battery, these ions move back into the cathode, moving the electrons in the electrical circuit, thereby providing the power output that we need. Now, the process in which these lithium ions go and insert into the material is called as lithiation. Here are some equations that are involved in these batteries. You have cathode, anode, and the overall chemical reaction that goes on in these batteries. Now, and as there are advantages, there are also challenges here. And so the challenges involved are mainly if you think about taking a sponge, for example, and trying to clean a spill of water. The first time it works great, but then if you keep repeating taking out the water, draining it out, then again using the same sponge to take out the water, you will notice that the surface of the sponge degrades over time, and eventually the sponge will not be able to perform the same functionality as it was the very first time. This is exactly what happens when we use our cell phones. A new cell phone purchased may give out like 8 hours of battery charge the very first time, but 6 months later you will realize that it only now gives out for 6 hours. This is because of the area that is involved in these batteries now loses the electrical contact, thereby losing your energy output in the battery. So the main problem involved with all these batteries is there is a lot of structural and conductivity changes that happen during these lithiation procedure. Now, moreover, this is something that we are not seeing so far is lithium is a very rare metal. Sooner or later, it's going to go away, and all these lithium-based batteries, the price of them is going to rocket. In addition, mining lithium is not easy, and along with that, doing the manufacturing of these lithium is involves a lot of challenges as well. Now, the other important challenge with the lithium-ion battery is coming to the safety. You would always see when you try to ship your phone or something, there are warnings mentioning there is a battery involved that you're trying to ship. So further, giving an example, you must have heard of the Boeing Dreamliner incidents where the batteries exploded. So these batteries caused a short circuit because something called as a dendrite formation in these batteries. So dendrite is this solid electrolyte piece of the battery that connects both cathode and anode, thereby short circuiting the circuit itself. So these are several challenges that we already know for a lithium-ion battery. There is a lot of research that is currently being going on to try to improve these lithium-ion batteries. But due to the main important challenge that the battery, the lithium itself, will not be available easily. So the research started focusing on using other materials, like I highlighted here. This is listed in one of these journal. So you have different combinations of cathodes, anodes, electrolytes that are being worked on as an alternative to lithium that can work the same way as a lithium, that can give the same energy output as a lithium and perform better or safer than a lithium-ion battery. But these new materials, there is a lot of research that is needed. Even the lithium-ion battery, it took time after its discovery in 1990 to get to the point where we are. So these new materials, for application in batteries, it's not easier, and it is not straightforward as we think it is. So the immediate practical purposes, the immediate future alternative batteries that we see will still use lithium, but they come in the form of lithium sulfur or lithium air batteries. And there are flow cell batteries. So all these are the very recent upcoming future batteries. The reason why the research is still focused on lithium is because it's already studied so well, like I said, since 1900s, 1990. And there are a lot of research articles put in to understand what goes in the mechanism in the battery. And they studied what are the safe guards that we can take. So there is plenty of data already available and precautions that we can take to make sure what we can improve on the lithium-ion battery. Now, one such improvement, in particular in the recent years, we have seen is using nanomaterials. I'm going to discuss further where nanomaterials come into picture, but this is like a graph showing all the comparison between where we started with a lead acid battery and where we are now with a lithium-ion battery, and what do we expect in the future batteries out of a lithium oxygen and lithium sulfur kind of batteries. So as I mentioned, these nanomaterials, so the nanomaterials are really small, very much tinier than your hair. They really try to help the performance of these battery materials. So the key here I'm highlighting is to understand what goes in the material at these atomic to nanoscale levels to realize what changes they make, either additive or they cause any further challenges. So we need characterization techniques at these atomic to nanoscale levels to determine the exact problems. So this is the focus of my research in my PhD, where I was trying to come up with characterization techniques that can study nanomaterials in particular that are used for battery materials. Just to give further background on nanomaterials, why they give. So, like as I mentioned, they're really small. So, being small, they have a shorter diffusion path for these ions or electrons to move inside the material that I've showed earlier, where you have ions, lithium ions, and electrons move inside a battery. So, being a shorter path, which means we can charge your battery, discharge your battery much faster than a regular battery. So, that's one advantage. The other is nanomaterials, though they are small, their surface area is much more higher compared to a bulk material. This will be particularly useful when you want to dissipate a lot of energy in a small amount of time. So these are a couple of main points, and then I've highlighted a couple more particular to the batteries. We talked about these mechanical changes. So it is studied recently in multiple types of nanomaterials that these materials give better accommodate the strains and provide better strength in the functionality of a battery. Just to give an example, I have a graph here. This is an iron disulfide nanomaterial battery, and you also have a bulk material battery. So the blue is the nanomaterial involved battery, and green is the bulk material battery. And you can clearly see that there is a lot of difference in the output, the capacity, and also the energy density of a battery when we add these nanomaterials. The main disadvantage of a nanomaterial is they're really small, and the techniques that we already know, and probably some of the other speakers already discussed, like XRD, you have electrochemical cycling. All these techniques, they only give you the average data for a particular mass of the material that you're studying. They cannot give you at the atomic or nanoscale level so easily for any material. Moreover, nanomaterials, they try to agglomerate very easily due to the van der Waals forces between these on the surface of these particles. So these are some challenges that we want to avoid when we work with nanomaterials and further design for different applications. Coming back to lithiation, so as I mentioned earlier, lithiation is the process in which you're inserting these lithium ions, taking into the material, and you're taking out of the material. So here I wanted to show, coming back to the example of the sponge I gave or your battery. So this is a regular plain silicon film, which went through the first graph is a 1 cycle and the second graph is a 30 cycle of your battery charging discharging cycles. As you see, some of the material lost contact with the surface area, thereby the output of the battery reduced eventually after 30 cycles. And this is how we can visualize on a nanowires. So nanowires, when you carefully design, grow in specific directions, and when they undergo these lithiation procedures, it is known that they can withstand better and they can grow in a particular direction, providing a known strength of the material. And I mentioned about different pieces in the batteries. I wanted to highlight like where nanomaterials are in terms of batteries. Like they're used almost in every piece of the battery now. There is a huge research that is currently undergoing to determine how these nanomaterials can perform. Recently, graphite, the magic material, is very well used in pretty much every piece of your battery. Here, I just highlighted this one design of the battery that I really liked. It's a pomegranate shaped cathode battery that someone came up with. It is very interesting how one person is able to design these batteries. He found that so in a battery, in a battery during charging discharging, we have something called as a SEI, a solid electrolyte interface formation between anode and the electrolyte. This formation actually causes a lot of degradation of the energy density in a battery during your cycling. So using this pomegranate design, this researcher was able to perform a stable interface and thereby increase the life of the battery. So these are just some examples that I wanted to show where everything is, how nanomaterials are being used, and uh, why the nanomaterial study, understanding at a single level, is really important. As I mentioned earlier, all the techniques that we know, the characterization techniques, they can only give the average of the information. So to the real goal lies in understanding at a single nanomaterial level. I wanted to highlight one more example here that will clearly show. This is a transmission electron microscope graph. This is a tin oxide nanowire inside a transmission electron microscope. You have a lithium cobalt oxide cathode, you have a tin oxide anode, and a ionic electrolyte. So initially, when we started charging, the performing the similar procedure of a battery where you charge and discharge. So inside the transmission electron microscope, what we observed here is, as you see, the length of the nanowire drastically increased, and also the volume of the nanowire increased quite a bit. In exact terms, the diameter increased by about 45%, and the length increased by 60%. So these are some key changes that one can observe when you study a single nanowire at a time. Now, TEM, as we all know, the sample preparation is not easy. And moreover, this kind of experiment only works for anode materials, or to study anode materials. It is not possible to study a cathode material due to the safety of the lithium. Lithium can explode. And moreover, using a transmission electron microscope, it can only give the morphology, how the nanowire would look like, as you see in the graph. And further, it can only give the composition change, like what is the percentage of carbon, for example, between a point A and point B. So these are some information that a TEM can give. But if you see in a battery, we talked about the structural degradation. So this TEM measurement cannot give us like the mechanical property or what is the capacity degradation that involves with a change in the structure with lithiation in the battery. So these are some of the existing challenges. Each technique has its own challenge, especially studying these nanomaterials. So to come up with a new method, we design what we call as a nanowire electrochemical cell on top of a silicon chip. So on this chip, we deposited nanowires, single nanowires at desired locations. And on that nanowires, we then performed lithiation experiments and then came up with techniques, characterization techniques, to measure electrical, electrochemical, and mechanical properties of these nanowires. I'm just gonna give a couple of slides on my fabrication technique just to show how it's done. So this is on a 4-inch silicon wafer. A silicon nitride is deposited initially, and the design itself looks something like this. So on the left, we have a biasing electrode. It is a single pad, whereas on the right, we have these individual pads, and each of the location is a individual nanoelectrode locations. So each 4-inch wafer can give about 200 chips per wafer, and each of the chip will have this design with about 200 and 400 device locations on it. These are some more information that I just put in. So I performed all these experiments in a Department of Energy facility where the research equipments are really sophisticated and really advanced. These helped gave us the designs in terms of very few nanometers. Like the gap that we are talking about is about 400 nanometers between the electrode. I will show further images regarding these. So this is how the 4-inch silicon wafer would look like with different designs as fabricated. So further giving more information, it involves a two-step photolithography process. The first step involves developing these bigger pads, and then the second step of photolithography involves electron beam lithography, then liftoff, and then focusing on particularly the gap locations, the electrode locations. This is a scanning electron microscope image of that small location that we saw in optical image. This is the scanning electron microscope image. As you see, the nanowire perfectly centered at the center of the electrode, and then we perform additional tests to characterize whatever we need. So this is another nanowire that is deposited. Now there are some horizontal bars that you see. So this is another characterization techniques that I've used. It's called EBID, electron beam induced deposition. There are a couple of things that these vertical lines or the perpendicular lines do. One thing is to hold the nanowire in place in the same location. The other is to provide electrical contact of the nanowire to the surface. I'll talk further in detail regarding this. So as a question, how I'm able to deposit these nanowires. So I've used a technique called as a dielectrophoresis, or shortly called as DEP. So DEP is if you place any polarizable particle in a non-uniform field, and depending on the field that you apply, either a strong positive or a strong negative, these particles can experience a dipole and thereby attracting towards one side of your electrode. Either you want it towards the positive or either you want it towards the negative. So this whole procedure or process is called as a dielectrophoresis. So in my experimental technique, the chips that I have shown earlier, I've inserted the chip in an ethanol solution in which I put in several nanowires, and I've applied bias between the biasing electrode and the unbiased electrode, thereby causing these nanowires to come and deposit exactly where I wanted. So here in this, I'm showing a lithium iron phosphate nanowire that is deposited between the locations. Coming to the principle of the DEP itself, this is the equation involved. I'm not going to go much into detail, but what I will highlight here is there are some parameters that you can control to figure out how many nanowires you want at a location, at what location, at what region that you want. That is called as the permittivity, the region that defines the ability of the particle to be polarized. And further, we have in here the voltage, we have the solution itself, how distributed the particles are. So these are several of the factors that I've listed here can affect how your particles can deposit in those locations. So out of this, what I've focused mainly are the voltage, time, frequency. These three parameters have found to improve, or they found to influence more how your nanomaterials are deposited. So here I'm showing several types of nanowires, or I would say nanomaterial systems that I've deposited. The first one, as you see, it's a very large lithium iron phosphate. The second picture is an alpha MnO2. It's a material system that I'm going to talk about further in detail. The third one is called as an acid leached alpha MnO2. Acid leaching is one of the synthesis technique that is used. I will talk about further on that. The fourth one is a graphitic nanoparticle that is derived from lignin. Then the next one is a sodium manganese oxide nanowire, then acid lead sodium manganese nanowire. Then I've also deposited some nitrogen doped carbon nanotubes. Then I've deposited some indium antimonide. These nanowires are very useful in developing next generation magnetic materials. And last but not the least, the last one, if you look carefully, you have additional pads on top of the pad, and the nanowire is sitting on top of the pad. So it's a three-dimensional configuration that we were able to achieve. And the nanowire itself is also a tri-layer nanowire. You have indium antimonide, nickel, and then indium antimonide nanowire. So these are several nanomaterial systems that I worked in my graduate study. Deposited. I've worked with all these parameters, analyzed, then characterized them for different applications. So among all these material systems, I've particularly chose alpha MnO2 material system. So as I talked earlier, lithium is scarce. It will not be available easily in the future, and we will have to find an alternative. So alpha MnO2 is one such alternative. It's a green material system. In the sense it is very environmentally stable, it's readily available, abundantly available, and moreover, the structure itself is plays a very important role. So the crystal structure is you have a alpha MnO2 with a manganese lying inside. Inside the purple, the big purple that you see is your manganese, and you have these octahedra, the oxygen on the outer shells. The shape itself plays a big role in how this material system will be used in the future. I will talk further regarding these. I have some images of the characterization. So this synthesis is performed by our collaborator. They developed these nanomaterial systems and they have given it to us. And I worked on depositing, then studying how these nanomaterial system performs. The only drawback that we have seen is though the crystal structure plays a huge role and huge benefit, we also notice that the structure itself can cause a very poor cyclability of this material system. So I'll talk further on this material system and why I'm saying the cyclability is poor and what can we do to improve this material system. So doing step by step, I deposit this nanowires on the chip, as I talked about earlier. Then I mentioned about this technique called EBID, electron beam induced technique. Once all this done, the very first step involves lithiation. So the lithiation itself is done inside a glove box because lithium can explode. It's a harmful chemical. The experimental setup involves putting the chip in an electrolyte and having a lithium wire that acts as an anode, and the nanowire itself will act as a cathode. Once we apply the electrical bias needed, that will either charge your nanowire or discharge your nanowire accordingly. So in all my experiments, I've performed a unlithiated test. Then I performed a lithiation of 2.75 volts, a 2.25 volts, 1.5 volts degradation studies at each of these lithiation cycle, and performed different characterizations to measure the electrical, electrochemical, and mechanical properties of these nanowires. So we saw that example of the TEM, where during lithiation, the nanowire experiences a lot of structural changes. So to determine these structural changes during lithiation, I've opted for using the atomic force microscope. So in this figure, as you see on the left, is a pristine nanowire, pristine in the sense it is as synthesized. Then the next one is post lithiation. And I've used the AFM plots to measure the diameter of a nanowire. And this is how it would look like between lithiation and unlithiated nanowire. You will be able to clearly figure out that the nanowire keeps changing in size when you start lithiating a nanowire. Once the lithiation is complete, so here I talk about the electrical characterization, how I was able to measure the electrical, um, the voltage and current inside this nanowire in a single nanowire. If you remember recall the design that I showed, I have a large pad on the left and there are individual pads on the right. So these pads, I connect these probes and use a source meter carefully using optical microscope. I make a clear contact, and thereby I will be able to measure the current and voltage using a two-step uh, analytical technique. So I have this equation, which is derived from the regular equation that we use to calculate the resistivity voltage in a particular circuit. But here what adds is your contact resistance, RC. So to measure this, so what I did is I've used two different inputs, and I get two different outputs, known outputs that we can measure. And based on that, so two inputs, two outputs, you will be able to measure the unknown parameters. So as you see here, there are two different nanowires that I know the diameter of. So these nanowires are really small. It is a challenging effort to measure the nanowire. So the National Institute of Health, they have this very interesting software called ImageJ. Using that, you will be able to measure the nanowire very carefully to the approximate calculation. The NIH, the software itself is used in the medical field where they want to measure the diameter of the cells. But the software is so generic that you are able to apply for multiple fields. So once I know the diameter, once I know the uh, current that is output from each of these nanowires. So I have two equations, two unknowns. I was able to solve what will be the contact resistance involved and what is the conductivity of this material system. So the experimental setup is very easy as it looks, but it's very challenging to make those contacts at the right locations. You really need to know where the probe is going. You can easily damage your nano electrode locations. So here is a graph at all these different stages of lithiation that I talked about. And you can see that the more lithiate that you do, the nanowire, the output from your material system degrades quite a bit, which is what you see in your battery, right? When you discharge your battery quite a lot at 5%, then there is nothing left in your battery to give out any power. So these are some measurements, electrical measurements that are performed. So what information that we can gain out of this is as we increase the lithiation, we see an increase in resistance, thereby a drop in your conductance. Now, there must have been a question. If I go back, I talked about in the experimental setup, in the lithiation itself, there is an electrolyte involved. Now, the electrolyte can impact the nanowire technically. But the beauty of the experimental setup is that when we did just the electrolyte measurement, we did not really see any change before and after on the nanowire. So thereby we eliminated that the electrolyte can cause any effect on the nanowire. So the I cannot hear your question well. Can you repeat? Hello.
If there is issue with the unmuting, you can just type in the chat box.
All right, we can come back to that question at the end. Then, So this is what I talked about. The electrolyte itself was found to cause no change in conductance. So the electrochemical measurements sound really easy. Here comes the tough part on this nanowire, how I can perform the mechanical calculations or calculate the strength of the nanowire or nanomaterial, particularly during lithiation. So this I would say was the most challenging part of my research. As we talked about earlier, during lithiation, there is huge change in your material. There is a lot of structural degradation. The material can undergo fracture. They lose contact with the ground. So there are several changes that happen in a material during lithiation. Now, you must have heard about recent materials in batteries, like using silicon, sulfur. The main drawback of these materials is the very first cycle, they undergo about 200% reduction in capacity. So there is a large structural degradation that happens in these new material systems that we are trying to reach and implement. So the goal here is to understand how each of these failure mode occurs in a nanomaterial system, how we can determine it, and how we can control it to build better batteries. Um, Now, in research community, there are several techniques established to perform material mechanical property measurements. Like these are some of them. Using a mechanical resonance, you resonate the nanowire with a known frequency and thereby record the strength of the material. Then you have a three-point bending method. It's a very well-known method in solid mechanics. And then you have a nano indentation technique. This is also very well known. Um, and further, there are several researchers creating up with these mathematical models using density functional theory or some other theory where they want to measure the property of these nanowires. Now, though there is a lot of research that is ongoing, there are quite a bit of drawbacks in all these techniques. The drawback itself is, for example, if they are studying using a three-point bending method, in the experimental setup, the nanowire is not hanging uh, as a bridge like what I shown in my experimental setup. They lay flat on a surface and you do a three-point bending on that. So the output or the measurement is not accurate given that these nanowires are really, really smaller in diameter. And moreover, in the mathematical models, as you all experience, you try to give some known parameters, you fix some of them as constants, and then you try to calculate something else. So the measurements itself are not really accurate. They don't give the real information of a nanowire. So I want to share the technique that I've used. So the same chip, where the nanowire is deposited, as you see, it is like a bridge. Your nanowire is suspended with nothing holding it in between. So the three-point bending using an atomic force microscope, where I'm using the force from the tip of a AFM on the nanowire at desired location, will give the exact calculation involved in the deformation of the nanowire based on the deflection recorded on the laser. So this is a based on the contact method of your AFM technique, where you place the AFM tip on your nanowire, you bend it to a certain distance, thereby recording the deflection on your laser. That is your graph that you get from your AFM output. Then analyze the output of your AFM to a mechanical evaluation or calculation involved. So what I did is, as anyone with an AFM will know, a contact mode does not give a good screen, but it gives a good force displacement curves, whereas a tapping mode gives a real good, beautiful pictures. So I've used tapping mode first to get my image of the nanowire. Then I go into contact mode to exactly insert the force where I need on the nanowire. Further talking on the experimental setup, this is how the force output on the AFM curve would look like. You have a retract curve, you have a approach curve, then you have someone with your mic. Yeah, sorry. So the difference between the curves will give how much of the force is acting. And as you all know, this is the famous Hooke's law. You insert a force, you know a displacement, you can calculate the stiffness of the nanowire. I've used the same technique here to calculate um, the displacement of the nanowire. And once I know the displacement, the force acting on it, then we have a formula to calculate the Young's modulus that gives out the strength of the nanowire. So this is the experimental setup involved in measuring the Young's modulus of the nanowire. Now it really looks so simple, but measuring the nanowire diameter even to the single nanomere can make a big difference in your Young's modulus calculation. So it really depends on how accurate you are able to measure your diameter of the nanowire. Now, further, nanowires are single dimensional structures. They don't behave the same way as we think they do. So, for example, I talked about using the atomic force tip to press on the nanowire. What if, how do I know that I'm pressing exactly at the center? So you really need to understand how these graphs look like, how the approach and retract curve are tracing out each other. That can tell you if you're exactly inserting the force at the center or on the edge, or if it is slipping on the nanowire. That's one thing. The second is nanowires are really small, and AFM tip, you have to choose the specific tip that is applicable for your nanowire size and shape of your nanowire or nanomaterial. That's the second judgment that you need to make. Then the third is how much you're pushing will matter in terms of the nanowire strength. Every nanowire, though they are suspended, they may not stay suspended. They can sag a little bit, they can deflect a little bit, or they can even break. So I will show some scenarios of those and how we are able to use that data and to measure the information that we need. So after Young's modulus, the other important mechanical parameter that we can measure is the ultimate strength. So the ultimate strength that we can define is the strength that is needed to eventually break the material. So here is an example of the approach and retract curves on the AFM look like when you break the nanowire. So the tip is extending its force, and then the nanowire is resisting, but at some point it breaks and the tip just retracts. So this is a significance of the curves. So depending on the data that you obtain, you can measure or you can extract the information that you need from these AFM curves. So here is a equation that will give you the calculation involved in measuring the ultimate strength of a nanowire. Now this Young's modulus and ultimate strength are really easy in terms of how the calculation is performed. But the third scenario where I talked about how do you know if a nanowire is sagging on the, or your AFM tip is causing the nanowire to bend in a different direction. So all these nanowires, because they are really small, they experience something called as non-linearity. Now the model itself is established as an analytical model in your bending and tension models. But however, to measure, it requires a little effort on the force displacement curves. So here I will show a couple of examples how this measurement is done. So if you clearly notice how the approach and retract curve are there in terms of force versus deflection, you see a small difference. You have a plastic deformation that can cause when the nanomaterial is undergoing both
You
tension
have
and
now
also
equipment list.
deflection.
Last time you prepared equipment list.
So these plastic deformation, what I do is I make a model based on how it should look like, and then I put in the experimental data, how it came to be, and I subtract the data to give how much of the deformation each nanomaterial is undergoing through. Now, in addition, using the techniques that we have developed, we can calculate something called as the theoretical strength, that which gives how good of a material it is for a particular scenario or for a particular application, which is given by Young's modulus divided by 2 pi in general. So these are all different mechanical parameters that I was able to obtain on these structures. So here is an example of a brittle fracture on a nanowire using an AFM tip. So these are three-dimensional AFM plots. On the left is the nanowire before, and on the right is the nanowire after breakage. So we talked about different characterization techniques. I've showed how electrical measurements are performed, how electrochemical measurements were performed, and then finally how I was able to do these mechanical measurements. Now, the next important technique is to replicate or do a fast forward on all my techniques at once for a single nanowire. Like in your battery, you constantly charge, discharge your battery several hundred cycles throughout the life cycle of a battery. So I wanted to set up an experimental study to analyze how a single nanowire would look like in for example, like let's say 5 cycles or 20 cycles or 100 cycles. So that was my next experimental study that I have done. So just to give a little background, what I was talking about, we call it as a degradation study. So I gave a couple of examples earlier, particularly in silicon sulfur type batteries. The very first cycle itself, you would see a lot of mechanical degradation in your material. Now, in your cell phones, for example, over several hundred cycles, you see that your charge in your battery drops. So I really like this particular slide. So overall, during a lifetime of a battery, you would see that the capacity keeps dropping. There are several reasons for it. So this particular image, I really like it. It shows every single problem that involves in a battery. For example, you have binders that can lose, that can crack. You have a solid electrolyte interface that forms at the anode. Then you have a separator material that can, if not stopped, it can cause these dendrite formation. Then you have your cathode material that can break. This is what happens in your sulfur and silicon batteries. So I like this picture. I keep using this. It gives you, in general, all the different issues that actually goes on in a battery. So in my material system that I've used for one cycle, I've I have extended it for one cycle, and I have extended it for 20 cycles. And I wanted to see how the material performs at each of the charging cycles, how it behaves at a charging, how it behaves at discharging, and I repeat the number of cycles at each point. So I chose the 4 volts as my charging voltage and discharging as a 1.5 voltage. And at each of these steps, I measured my previous mentioned techniques, electrical, mechanical, and electrochemical measurements at each of this. So let's see how that study came out to be, and I will talk about some interesting things here. Um, so this is all, this is just gives a brief of everything that I've talked about earlier: depositing nanowires, then EBID, then lithiation, then electrical measurements, then mechanical measurements. So this alpha MnO2 material system, it really behaves differently. So I told you, I am mentioning earlier, the crystal structure of this alpha MnO2 plays a real good role in why I chose this material system. So it has this gap in the crystal structure, and when you do the first discharge, where the lithium ions try to come and sit in the cathode, as you see during the first discharge, the lithium tries to occupy the lower energy tunnel walls in the crystal structure. So the crystal structure uh, started with this, but after the first discharge, the lithium ions go and occupy equal spaces, the lower energy tunnel surfaces inside the crystal structure. This contributed to a increase in your mechanical strength of the material compared to the original material. So this material system really behaved differently compared to what we usually see in a first charging cycle. I think to give further example, you must have seen earlier that when you buy a new cell phone, they recommend charging it fully for the very first time. That is to improve the behavior of the cathode and anode materials in your battery system. So what here lithium does is it tries to, you may question why it is not going to, like, let's say 12 o'clock and 6 o'clock position. That is because there is some reflection or repulsion between the two, so it tries to occupy equally on the opposite side. And based on the measurements for each of the cycle, I was able to see that at the first discharge, you see that the Young's modulus is really super high after the first discharge. And then eventually it keeps dropping. And then I noticed that at 20 cycles, it again increased depending on how the structure goes. So here I just talked about the Young's modulus and experimental theoretical ratio of the material at each of these discharge cycles. As I talked about, it increased further first, then it decreased, then again it increased at 20 cycles. So these are some of the observations that was made in this material system. And similarly, we can study any material to understand how it behaves at different cycles. But remember that this is all on a single nanowire. So that's the beauty or advantage of my experiment. So to conclude, I've shown how we were able to perform fabrication of a single nano electrode, and once we do that, how we were able to carefully deposit nanowires using the electrophoresis. Then I've talked about how we can perform different measurements on each of them. There are several more ongoing projects which I did not talk about. Is using a three-dimensional structure, we can create a resonance in the nanowire, thereby measuring how much lithium is there in a nanowire at a particular measurement. So there are several contributions made in my research, and this was I've reported the first study in several nanomaterial systems, the electronic conductivity, and also the mechanical measurements that were previously not there in literature. So these are all some of the outcomes of my research. Some of the future directions are, like I said, to use a nanoresonance technique. Then there are techniques to develop simulations based on the experimental models and analytical models to accurately measure the behavior of a material. and further to understand what goes on at each of these nanomaterials at the surface level. You can, in an AFM picture, you can see how the surface behaves with each of these lithiation techniques. I have more to talk about, but I'll just mention some of my publications and some of my conferences I gave. I just want to thank a couple of people that I've worked with over the period of time. So that concludes my the graduate research that I've done, but I've wanted to mention a few more slides regarding the importance on whatever I have done. So in the upcoming future, you will see nanomaterials will be a part of life. Even now, uh, even for example, in your let's say the soap or the body wash, they have these nanomaterials already involved in them. Either the face creams that you use, they have nanomaterials involved in them. So their applications are growing numerously. So as more and more of these keep growing, there comes a point where you really need to understand how each of this material system is performing, how each of them is behaving. In addition, there are a couple of examples that I wanted to highlight from research. I didn't list the references here. So in the future, you will see that that there will be nano robots. These will be a functional robots out of a single nanomaterial system that can go in your body and target, let's say, one particular bad cancer cell. So these will be the future of nanotechnology in real-time applications. On the right, I have listed how one single nanowire was used to in sensing applications, like how you were able to measure, let's say, a percentage of hydrogen, a percentage of carbon in atmosphere, or things like that at a single nanowire level. Then I have some more examples I mentioned earlier regarding this. Indium antimonide is a beautiful nanomaterial system that has huge applications in magnetism. It has so much benefit that you don't need so much energy to switch the bands in that material system. And then further, you see here, there are people who are synthesizing quantum dots using nanomaterials. Here it's a gallium antimonide material system for different applications. So as I talk more, you see nanowires, nanomaterials. They have numerous applications, and there is a real need in characterization techniques to measure accurately the properties of these nanowires at a single molecular or atomic level and understand what really goes on in these material systems. Just to add a little bit more on the nanotechnology and how it applies to where I am working on, I'll give a brief on the history of transistors to begin with. So as you see, the transistors began in 1970. We are almost in 2020, and over the generations, there are like several types of transistors that came now, and you see how the number of transistors increased in a particular space. This is all possible due to the different research you all are doing, everyone is doing, contributing to the scientific community in some way or the other. And that knowledge is applicable for various industries. And you can clearly see in the last 10 years, there is a huge jump in the number of people who are involved in developing these different types of microprocessors for different applications. These microprocessors have become a part of life into each and every application that you work with or you deal with. Now, The reason I'm mentioning all this is the technology involved in it is called as the FinFET technology. So we started the transistor with a single gate, and once you switch the gate to a vertical place using a FinFET technology, now all these current players in the market are able to achieve a lot of performance. So going forward, we will begin using nanowires, nanosheets, and these are the upcoming future where you will see applications going into transistors. Otherwise, we cannot keep increasing the number of transistors following Moore's law every 2 years. So Moore's law is what the industry follows. The number of transistors they want to double every 2 years. But currently we are hitting a limitation in the sense right now the technology is 40 nanometer, and the latest technology that will come is 10 nanometer, and then the next one is 7, then 5, then 3, 2, and then 1.4. As you see the dimensions decrease, you will see that more and more nano applications will come into picture. You will need a lot of new characterization techniques to figure out how you are able to determine that yes, I know my device is working correctly. So there is a lot of scope in characterization. There is a lot of research there are different people are working on. That's why I brought up one more slide. For example, you must have heard about machine learning, deep learning. There is a lot of data that is being analyzed currently. You save the data, you keep reusing the data for different applications. So those all will be the future. Everything that you do, everything that we are doing, small bits and pieces, they all contribute to a bigger picture in the future. So once the nanomaterials we are able to achieve, then the future will be quantum processors, techniques, and we will apply that for different applications. That being said, I believe I've covered what I wanted to share. I just wanted to share this beautiful slide. It is a phase map that shows in different chemical reaction how the, like you see how inside the material the structures are changing with lithiation. That being said, thank you very much for your attention. Any questions I can take?
Yes, participants, if you have any questions, you can unmute yourself and you can directly ask to the speaker. So in the meanwhile, I have a query, sir. Like you were talking about the lithium ion and the uh, alternative to that lithium ions. Like
Mhm.
right now, even magnesium ion is said to be an good alternative to lithium ion. How far
Yes.
it can sustain in terms of
So
efficiency, like lithium ions?
it will not. So to really answer that, let me show the slide. Um, initial graph I had. So this graph tells a lot of information on each of the material system that we are dealing with. Yes, this. Sorry. Okay. So you talked about magnesium, right? So magnesium should be somewhere much below manganese oxide. I don't even see them. So so this is the graph compared with lithium, and you see that magnesium is nowhere in the picture, which means that the possibility of that replacing lithium is really low.
Okay. Anybody else?
there some questions typed in, or? Okay, I don't see much. Feel free to ask anything. I mean, maybe not relevant to this topic as well.
Hope everything is very clear to them.
I hope so.
Ajay, you have any query? You have unmuted yourself.
I think I might have finished much sooner than I thought, correct?
Oh, no, actually, we have another session at 11:15. So,
okay.
So if there are no more queries, see, if you have any queries still, and if you want to ask the speaker, you can write to him, to his email. Okay, so that it will be very clear for your whatever doubts that you have. And finally, let me thank Dr. Naveen Kumar Reddy for sparing his valuable time in spite of his very busy schedule. Being in US, and right now the time is too late for him also, but still he has very graciously accepted our invitation and shared his experiences and the knowledge that he has gained over the years. So I would like to thank on behalf of our department and the university for the very wonderful lecture that he has given. So I would like to thank you, sir, once again. Thank you very much for your valuable time.
Bye all. Thank you.
Okay, one question is there. Dr.
Okay.
Naveen, yeah.
Yes.
There is one question from a participant, like magnesium compound is present above MnO2, like.
Is it in my picture? I may not. I may have missed
like
it.
it is.
Oh, I mean, it's a lithium. Yeah, it's a lithium compound. Yes, it
compound.
is.
Yeah.
Yeah. So compounds, yes, definitely it can, but magnesium by itself, it will not be able to.
Okay. Fine, sir. Thank you very much, sir.
Yeah. Thank you.
Okay, participants. Now we'll have a session from Dr. M. Papa Rao. Okay, let me introduce the next speaker. Dr. M. Paparao is a scientist from Jawaharlal Nehru Research Center. So Dr. M. Paparao received his PhD at IIT Madras in the Department of Metallurgical and Materials Engineering. He worked as an assistant manager at Jindal Steels Limited, Karnataka during 2015 to 2019. He has more than 5 years of experience in new product developments in the field of steel industry and aluminum industry for automobile applications, and more than 10 years of hands-on experience on sophisticated equipments like PEM, SEM, and EPSD. He is the editorial board member for the International Journal of Metallic Materials and reviewer for the Journal of Materials and Manufacturing Processes and Journal of Material Science and Energy Engineering. He has published various research articles in reviewed journals and conferences. Including... Somebody can mute the mic. Yeah. So he has published various research articles in peer-reviewed journals and conference proceedings in Elsewhere and Springer. He owned a patent on developing high-strength and high-elongation steel for automobile sector based on his research work carried out during his PhD. I warmly welcome Dr. M. Paparao for today's session. I request you to kindly take over the session, sir. Thank you.
Thank you, Mr. Mahesh. My presentation is visible?
Yes, sir. Yes, sir.
Okay. Thank you for giving me this opportunity for presenting characterization of nanomaterials as a part of emerging technologies in processing of advanced materials and its characterization. And first of all, myself, Dr. Paparao, I'm a scientist in the Jawaharlal Nehru Aluminum Research and Development and Design Center. It is from Nagpur. It is under the Ministry of Mines as autonomous body. So the outline of my topic today is comparison of light microscopes to electron microscopes, electron microscope, and resolution of the electron microscope, classification of nanomaterials, and sample preparation techniques for SEM and TEM, imaging by SEM and TEM, types of diffraction patterns in transmission electron microscope, and how we can index the diffraction pattern in TEM. So coming to the this comparison of light microscope versus electron microscope, generally in light microscope, the wavelength of the light will be from 400 to 700 nanometers. And for electron microscope like the scanning electron microscope or transmission electron microscope, so the wavelength is much smaller, around 0.0025 nanometer at 200 kV. So especially if you see in the light microscope, if it is etched with different etchants, so we can see in the color images. And suppose if you see in the electron microscope, it will be like a black and white or a gray in color. So the resolution in the light microscope will be up to, we can see not less than 200 nanometer, but in electron microscope, we can achieve 2 angstroms over 100 kV, but it depends on your magnification. So it is optical lens glasses. Suppose if you want to change your magnification, you need to change the different focal length of the glasses. So that you need to change the optical lenses. Suppose if you want to change in the electron microscope, the magnification, you have to change the current as well as, so that leads to the magnetic field. So then it leads to different magnifications. So the first transmission electron microscope was built by Max Nall and Ernest Ruska in 1931. That was only capable of, that time it was only capable of 6 times magnification, 16 times of magnification. So if you can see around the 1940s, so the best resolution that we could get was around 100 angstroms, that means 10 nanometers by TEM. But if you can see in the 2010, so that would be around 0.5 angstroms. So that is for TEM 05 transmission electron microscope. So people have been trying with the different combinations of the compound lenses to get the best resolution that can get. So the resolution is like the smallest distance that can be resolved with equipments or with our naked eyes. So that is called the resolution of any instrument or equipment. So coming to the classification of nanomaterials, nanomaterials are the ones which are in the size range of 1 to 100 nanometers. So we can classify the nanomaterials with various modes. Suppose if we classify the nanomaterials with like dimensions, so the 0-dimensional nanomaterials. So in this, all 3 dimensions are in the nanoscale. Suppose a nanoparticle. So all the X, Y, Z directions are in nanomaterial in size range. Suppose if it is in the 1-dimensional nanomaterials, so 1 dimension in nano scale, so those are and 2 dimensions in the macro scale level. So it is like nanofibers, nano wires. So some carbon nanotubes. These are one-dimensional nanomaterials. So two-dimensional nanomaterials in 2 dimensions of the material are in nano size and one dimension in the macro scale. So like nano sheets or thin films, these are the 2-dimensional nano materials. And coming to these 3-dimensional nanomaterials, so like a polycrystals which are in the grain size range in the 1 to 100 nanometers. So those are called 3-dimensional nanomaterials. So this is the classification of nanomaterials. Suppose if you see the gold particles, with these gold particles will have different kinds of shapes like nanocubes, nano spheres, and nanorods. So these are the 3 different morphologies of the gold particles, nanoparticles. And suppose if you see the titanium dioxide and the core shell of the oxide, we can see the nanoparticles here. And the last image is AFM image of polymer wrapped carbon nanotubes on mica with and these are some of the examples of the nano materials. So coming to the characterization, before characterization, first we need to prepare our sample very properly and carefully. So I have given some of the different kinds of nanomaterials in the form of powder, or suppose those are in the biological objects, and we see like how we can prepare these kind of nanomaterials for SEM as well as TEM concern. So suppose if you have a nano powder, how we have to prepare it for SEM analysis? So first of all, we have to grind our powder sample, then crush it, and then we have to take one specimen stub here. Okay, this is a metallic stub upon which we have to paste one carbon tape here. It's a conductive tape, okay, adhesive tape. Upon that, we have to sprinkle one pinch of powder and then blow dry excess powder from the sample so that any excess powder that is detached from the carbon tape, so that will be out after blowing. So then we can use this stub and it is ready for our SEM analysis. And coming to these biological objects, so you have a spider or ant or neuron or human egg, so or red blood cells. So how we can prepare these biological samples for SEM? So there are 2 methods. One is a conventional coating method and another is a graphene coating method. So in conventional coating method, what you do is we have to fix the material on the stub, okay, and then we have to like fixation. Upon fixation, we have to dehydrate that one, and then upon that we have to coat with a sputter coating or metallic sputter coating. So suppose you have a biological sample, you have to do the metal coating, sputter coating, and your sample is ready for the SEM analysis. And the other method is like a graphene coating. So where like there are some like graphene layers we have to prepare, and these graphene layers will be just floating on the water. Like the graphene layer, we have to keep it in the water. So and with the instrument, we have to fish the graphene layers, and these graphene layers to be kept upon the our biological samples. So then we have to keep it for next to drying. So that will be like then our sample will be ready for the SEM analysis. And coming to the bulk metals, like suppose you have aluminum alloy or steel or any other bulk material. So first of all, we have to make the bottom and surface, both the surfaces to be leveled. And then we have to use some emery papers with a grid size of 120 to 220 grid sizes. And Then you have to use some like a 600 grid size and then 800 grid size, and then you have to go for the diamond polishing with some different kind of velvet papers, and finally you should get a mirror finished sample. So suppose if you want to analyze your any inclusions or precipitate, like any bigger size materials, so you have to just you can use the samples for SM analysis as it is, or if you want to see some grain sizes and all, then you have to etch it with the proper etchant. And we also have to be very careful during the sample preparation. Suppose if you are using a bandsaw and your material is a copper, the depth of damage will be around 85 microns. And if you are using the grid size of 220 grid size, then the depth of damage will be 6.3. So you have to be very careful during the polishing of these samples for SEM analysis, because it may damage your sample and then you may not get original features in your sample. So, and that also, like suppose if you are preparing for etchant, the chemical damage also will be there involved. So you have to also take care of that to avoid any misleading features. So how we can prepare a sample for TEM, transmission electron microscope? There are several methods for several type of the materials. Suppose you have a nano powder, then a similar way you have to crush, the similar way you have to crush, like SEM analysis, how you have done it. You have to crush, and then then you have to keep the powder in the methanol or ethanol, and then use the ultrasonicator. Okay, so ultrasonicator, then after ultrasonification and it's uniformly, suppose the particles are distributed in the solvent, like a solution, then you have to take a filler, and then just keep one drop of the solution upon the copper grid. Okay, so here some of the copper grids, we can see that some grids here, and these are the nanoparticles what we can see under the microscope here. Suppose this is the nanoparticles, and this is the carbon block, and these are the features according to your sample. And suppose you have a coated material, so how we can see the cross-sectional or the thin film coating under the transmission electron microscope? As shown in this figure, we have to cut. This is a thin film coated upon the bulk material, and so you have to cut like this, and you have to make a tube, and then within the tube it has to go inside, so that two half circled blocks. So then we have to slice it with 0.5 mm thickness. Okay, so by using the dimple grinder, we have to grind the sample, and we need to use the iron beam miller, so to further thinning. So then the sample will be ready for the transmission electron microscope. Suppose you have a bulk metal, suppose, or a sheet or any kind of material you want to analyze under the transmission electron microscope. You have to first section like 0.5 mm, and by using the abrasive polishing or grinding, so that you have to thin it down up to 120 micron or less than 100 micron. And then suppose your sample is what is a soft material, so you have to make the 3 mm disc out of that, and then And then from 120 micron to 50 to 100 micron, so you have like a disc, so that you have to use a 1200 grit paper and then thin it down up to 50 microns and all. And then you have to use the disc grinder. And finally, that 550 to 100 micron sample, you can use with the electrolytic jet polisher or twin jet polisher, or you can also use a iron miller, so that the transparent region will have around less than 70, like 50 to 70 nanometer in size. So that is called a transparent region. Okay, so that is how we can prepare a sample from a bulk to transmission electron microscope transparent region. And you can also use some disc punches before. Suppose your material is a ductile material or your material is a brittle material. To making a 3 mm disc, we have to use ultrasonic disc cutter. And that's about a bulk sample like metals and alloys. And suppose you have biological samples and like sea algae or any other materials. So you have to just slice it, and then the sectioned picked up samples, you can keep it in the sample holder, which will be around 3 mm disc sample. So straight away you can keep it in the under transmission microscope, and you can observe the biological features, nano features under transmission electron microscope. So for that, the preparation will be first fixation and dehydration and embedding and then sectioning it. So this is how we have to do the biological samples. And suppose you have silica nanoparticles in SEM, so you can measure by some softwares which are inbuilt in SEM, and then from that you can also find out the size distribution of your nanoparticles. That means suppose your nanoparticles are in the range of 10 to 15 nanometer. That means most of your nanoparticles are in the size range of 10 to 20 nanometer or like that. So that we can calculate or analyze by the SEM. And these are the images of the gold nanoparticles, okay, in a transmission electron microscope. And you can see this white dashed lines delineates between the 5 different crystalline domains in the nanoparticle. So this is a 5-fold symmetry nanoparticle here, you can clearly see. And you can also see some lattice fringes, and the lattice fringes, the interlattice spacing is around 2.42 angstroms. And suppose you see in a gold nanoparticle, you can also see some twin boundaries. So both the faces are like mirror image of one on another. Suppose you have a nanowire, so so low magnification TEM is showing in the left side image, silver nanowire. And you can also see a high resolution transmission electron microscope of a core of a single silver nanowire. So this also has a 5-fold symmetry, where within that we can see some twins here, twinning in nature. So this can also be possible under a transmission electron microscope. We can also see the atoms by using some softwares clearly. And the cross-sectional images of the silica and the ZNO interfaces, you can see the ZNO thickness. So as I said, like the preparation of these cross-sectional image samples, and this is the imaging of the cross-section or thin film samples by transmission electron microscope. You can also measure your zinc oxide, the thickness here, 4 to 6 nanometers. And the rest is a silica. And suppose you have a silica with indium oxide interface, so you can also measure the thin film thickness under the transmission electron microscope. Suppose you have some biological samples like coronavirus or any other algae. So this the image was represents a coronavirus, where the color image, like color pictures, were taken by using some softwares. So with the mapping techniques. So suppose that depends on the coronavirus generally having the spike protein and small envelope proteins, and then nucleoside proteins and membranes of the proteins. Generally, the vaccine now, whatever is available at the present market, so generally it has to destroy all these proteins so that this virus can be collapsed or it can die. So this like vaccination, like vaccine invention also based on the by using the SEM or transmission electron microscope. So one can invent the vaccines by using these kind of equipments. And suppose if you see here, suppose if you can see these images are the virus images under a frozen electron microscope. What we have to do is like we have to freeze our sample, biological sample, and then cross section it, and then it has to be as thin as like less than 100 nanometer. Then only the features will be visible under transmission electron microscope. So here we can see these are the red are the spikes or crones, and the blue is like a nucleoside, some protein. Suppose you have aluminum, silicon, copper, aluminum alloy, and you can see some precipitates. Suppose you have done the aging at 190 degrees centigrade for 6 hours, and you have also aged at 350 degrees centigrade for 12 hours. So you can also see what is the difference or the kinetics of these precipitates under the transmission electron microscope. So you can see the red arrows indicates the discs which are in 90 nanometer diameter, and the blue arrows indicates the globular Al3Ti particles or some inclusion. Okay, and the green color arrow shows the globular needles. Okay, those are beta double prime phases. And suppose you have done this aging for a little higher temperature for a higher time, then what happened is this Al2Cu plates are becoming bigger, that can be seen, and also this green shape have, earlier it was 2 to 5 nanometer, now they're becoming 450 nanometer in diameter. So these kind of observations also we can find with transmission electron microscope. And also suppose you have a acicular precipitate at a peak-aged sample, so you can also see some these lattice fringes with atomic orientation directions also we can see 200 AL and 002. So that can also be identified by using the diffraction pattern. And suppose you have a carbon nanotubes. So in these carbon nanotubes, we have multiple walled carbon nanotubes and single walled carbon nanotubes. And you can also count how many walls in your carbon nanotubes. So suppose you see that 9 concentric walls are here in the left side my figure, and there is only one wall, like like only one concentric wall in the single wall carbon nanotube. And after getting this imaging, anyone can get that imaging, but how to analyze the transmission electron microscope? So in transmission electron microscope, we have different kinds of patterns. One is a spot pattern, ring pattern, spotty ring pattern, and diffused ring pattern, textured pattern, and double diffraction pattern. So before that, we see that ray optics of this in transcranial electron microscope. Suppose you have a sample here, okay. So suppose you say this is a single grain material. Within this single grain material, you have a different kind of planes. The red is in one, suppose 100 plane, okay. Those are oriented and parallel to each other. So 100 plane, and suppose this is 211 plane, this black one, 211 plane, and this is the optic axis we call. Once your transmission electron beam falls upon your sample, so this red one, which will be reflected and then falling on the objective lens, and then what happens is this will be merged here and converged here and then get a spot here. This is called a diffraction spot here, and this spot will happen at the backfocal plane, okay, this diffraction spot, and this yellow one will also give you, this yellow one means this is in the parallel to the optic axis, okay. So this is our transmitted beam spot, okay, and the violet one will give you another diffraction like the spot. So you have a diffraction spots here, since it is from the single grain, you will get a spot pattern here, okay. After that, this will give you an image. So here, whatever you see, this image will be inverted here, okay. So this whatever we see under the transcranial electron microscope, it is inverted and rotated. The rotation happens because of the helical path of the electron under the microscope. So that one. And coming to this diffraction patterns, so suppose if it is in the single crystal, we have a spot pattern. So you have a polycrystalline here, but your electron beam is only focusing on the one grain, you will get a spot pattern like this. And suppose you have a 3 grains here, okay. So you will get a spotty ring pattern. And suppose you have a polycrystal material and you have a ring pattern here. And you have a polycrystalline material, and if it is in the, and all the grains are in the nanometer level, so you will get a nano size, like you will get a ring pattern here. So this ring represents the nano, like it says that your grains are in nano in range. So these are some of the schematics. So here types of diffraction patterns here. Some of the textured pattern we say. Why this texture comes? Because if some grains are oriented in in a way similar in direction, so one spot will have a arc like shape. So you will have a textured pattern here. Suppose your material is amorphous material, and you get a diffraction pattern like a diffused ring pattern. And in your material, suppose half is amorphous and half is crystalline, you will get a spotty ring, like a spotty ring pattern. That means suppose you have a hydroxyapatite, which is amorphous in nature. That means you have a diffused ring pattern here. And suppose you have a crystalline hydroxyapatite. That means hydroxyapatite is 2 types. One is one is hydroxy powder, and powder with crystalline nature. So you will have spots with the diffused ring. So this is a spotty ring pattern. So you have a semi-crystal here, Suppose indium oxide layer you see. So you have a diffused ring with some spots, amorphous plus crystal. So after getting these diffraction patterns, then how we can index it? So we know that using the Bragg's law, lambda equals to 2d sine theta. So since lambda is much smaller, and if d is the spacing of the two layers are suppose 2.5 angstroms, and in transmission electron microscope, the theta will be always smaller than 0.2 degrees. So that becomes 2 theta equals to r by l. So then we say that r by l equals to lambda by d. Okay, so rd equals to lambda l. So here l is camera constant, and so since this lambda also is a constant, since it's a chromatic beam, like it's a monochromatic beam, the electron beam is. So this right side is a constant here. So we can see that r equals to 1 by d. Okay, so that L lambda is a constant. Suppose how we can index this diffraction pattern. There are the two methods by which we can index it. One is a camera constant method, another one is a ratio method. Suppose you have a diffraction pattern like this. Okay, so you will get actually a micron marker here that will be in the what is a 1 by a lambda in space, that is a reciprocal space. So that that scale already will be given on this diffraction spot. So you have to measure what is the R1 here, and R2 here, and R3 here by some software, or manually we can measure it, and keep the R1, R2, R3 here in these equations, so that you will get a D1, D2, D3. So these are the D spacings of this interplanar spacings of the materials, D1, D2, D3. And we have to compare these D1, D2, D3 with already available in data space. So these are the data available. So for suppose you are doing analysis for iron, so your lattice parameter is suppose 3.5, and your D spacing is suppose 2.7, you get a D1. So you can index that as a 111 HKL. Okay, HKL. So then suppose your D2 is 1.26, then you can index it like a 0.22. So likewise, you can index your spot pattern by using this data available in the books or in the softwares. And this is for BCC materials. Okay, so the same thing can be applicable here, and this is for PP material. And suppose that was if you already know the scale and all. Suppose you do not know the scale, simply you got a diffraction pattern from someone. They have already, like, they have given you the diffraction patterns. But so how we can index these things? So in this is we have to simply measure R1, R2, R3, and we have to do like it's a ratio method if you do not know the camera constant. So here R1, here R2 should be in the whatever the bigger one should be in the numerator, and the other smaller two are in the denominators. Okay. So if you get R2 by R1 and then R2 by R3, then you have to compare this. Suppose this is a R2 by R1, 1.414. So these are some of the R2 by R1 and R3 by R1. R2 by R3. So if your ratios are matching with already available, readily available patterns, then if the ratio is matching with this, and also if the angles also matching with this, we have to also check these angles. Then you can index the diaphragm, like you can index the diffraction spots as it is given in this figure. Or suppose your R1 by R2 by R1 is 1.155, and another R2 by R3 also is 1.155. Then you can index this one, and you can also cross check it. And one more condition is like it has to also satisfy Weiss zone law. So after getting all these HKLs, H1, K1, L1, H2, K2, L2, we have to cross check with this UVW. This is a zone axis. So HU plus KV plus LW, it should match with 0. So then your indexing of this diffraction pattern will be correct. So there are some 19 diffraction like patterns here. This for FCC, and the same will be for BCC. Okay, suppose you have a complex pattern. Okay, so you do not know so these things. So for simply is that if you have a complex pattern like this, you have to just separate the pattern 1 and pattern 2. So this is a square pattern and this is like a hexagonal pattern. And then you have to index this one separately and this one separately. And the same thing you can put it in this diffraction pattern spots. So that's all today. Thank you for giving me the opportunity to present this characterization of nanomaterials. And the session is open for any questions, please.
Participants who have any queries, you can unmute yourself and then ask, or if you have any issues with unmuting, you can even write in the chat box. Yes, anybody is having any queries? Participants can even write your questions in the chat box. Okay. Looks like the session is very clear and then in an easy, understandable way. So,
Okay.
Yes, Ravi Kumar, you have any question? Okay, fine. So, thank you, sir. Thank you for sparing your valuable time, and the session was very clearly understandable in very detailed way of sample preparations and all. So, thank you very much for your valuable time and sharing your knowledge on this occasion. And I would like to also thank Dr. Paparao for taking his time out in spite of all the odds that he had, and very enthusiastically trying to share his knowledge. So any participant, if you have any doubts or clarifications on characterization techniques, you can always reach out to Mr. Paparao, so who is very student friendly and enthusiastic person who tries to share his knowledge. So I take this opportunity to thank Dr. Paparao for his valuable session. Thank you, sir. Thank you very much.
Welcome once again.
Thank you. Participants, I'll share the feedback link of session 1 and session 2. Participants can fill the feedback forms of session 1 taken by Dr. Naveen Kumar Reddy and session 2 by Paparao. And again, we'll meet at 3 o'clock for the last session, followed by valedictory. Thank you, one and all.